last night's homework. And this one is a little bit more in depth, but it has some of the same ideas repeated again. So let's try it. Okay, so same instructions, but this time we've got a function x over 1 minus x cubed. And we're going to use the same sort of tactic that we just tried for the sine of 2x. We're going to try to find a Maclaurin series that's more familiar and have that kind of do the work for us. Unfortunately, there's nothing perfect. In that list of Maclaurin series that I told us we had to memorize, we don't have anything that's going to work perfectly for us, but we do know that this kind of looks like 1 over 1 minus x. X over 1 minus x cubed. Okay, well, we have a denominator, and it's 1 minus, and then, minus some variables. This time, for the one that's unfamiliar, we have x cubed. For the one that's more familiar, we have x. What we can try to do is we can try to use a couple of algebraic methods here to kind of go from this unfamiliar one to the more familiar one. So let's see what we can do with this. Okay, well, one thing you've got to remember is that 1 over 1 minus x is 1 plus x squared plus x cubed. This is just a infinite geometric series summation formula. And we do have kind of a pretty restricted interval of convergence here from -1 to 1. So that's one thing to be mindful of, that our interval of convergence for this whole problem is going to be pretty strict, just between -1 and 1. So keep that in mind. Okay, first thing I'm going to do is I'm going to repeat that trick that we did for the previous problem, the one we just did with sine of 2x. I'm going to do a little bit of a substitution. I am going to say, hey, wait a minute, I can take the familiar Taylor series that we already have derived, and I can replace my x's with x cubed for each of them. There it is. I can clean this up a little bit, and by cleaning it up I just mean that I'm going to replace x cubed squared. Let's rewrite that as x to the 6th. X cubed cubed. Let's write that as x to the 9th. Okay, and then that wasn't supposed to come on the screen so quickly, so let me hold off for 1 second. Okay, now that we've cleaned this up a little bit, you can kind of compare where we are now to where we want to be. And we're pretty darn close, right? Oh, that was a voice crack. That was another throwback to junior high. Sorry about that. Anyway, we're really close to where we want to be. We're at 1 over 1 minus x cubed. We're trying to get to x over 1 minus x cubed. So the only thing that's throwing us off is this tiny little x hanging out in the problem. Well, that's not that much of a problem, actually, because all I need to do is take the work I've done so far, and I can multiply both sides of my equation by x. Let me show you what I mean. Left side of the equation, multiply by x. Right side of the equation, multiply by x. And notice I'm multiplying this entire quantity, this entire infinite series is being multiplied by x. You might wonder, how do you multiply an infinite series by a number x? Well, it's term by term. So really, each of the individual terms is going to be multiplied by x. And it's pretty amazing because now, okay, 1 times x is x. X times x cubed is x to the 4th. X times x to the 6th is x to the 7th. X times x to the 9th is x to the 10th, etc. Our nth term is x to the 3n plus 1. That's our answer. I've got the first 3 terms, the first 3 non-zero terms just like they asked for, and I got the general term. That's our general term. And we've got our interval of convergence from -1 to 1. So it's pretty cool. That's how you do that homework problem, and that's kind of a general tactic that you repeat on that entire assignment. Now, one thing I'm going to do is, I kind of liked this problem. I like the function x over 1 minus x cubed. The reason I like it is because it's hard to integrate it, and so I'm gonna kind of take this function and build on it for another example to kind of show you another useful application of Maclaurin series. So let me go to the next slide, and you're going to see what we're going to do. And we're going to use the same function again. So we're going to expand on number 11 from the homework, and the instructions for this problem are compute the first four non-zero terms and the Maclaurin series for the function capital F. And I'm going to define the function capital F of x to be the definite integral from 0 to x of t over 1 minus t cubed dt. Okay, first of all, one thing that you might see with this integral is that it is a difficult integral to compute. Right, the integral of t over 1 minus t cubed dt, you're going to have a hard time doing things like a u substitution. For example, if you say if you say that u equals t cubed, then du equals 3t squared dt. Oh my gosh, I can't use a u substitution on this. I don't see a trig substitution, inverse trig substitution that we could do. This is a difficult integral to deal with. However, Maclaurin series are going to kind of come to the rescue, because I might not be able to easily compute this integral in terms of familiar functions, but what I can do is get a Maclaurin series that describes this integral, and I can use that Maclaurin series for all the same purposes I used the original function. For example, if I need to approximate the function capital F at a certain point, I can use, or actually not at a certain point, at a point between -1 and 1, actually an x value between -1 and 1, I can use my Maclaurin series to approximate that. Watch what I'm going to do. I'm just going to say that if I'm trying to take the integral from 0 to x of t over 1 minus t cubed dt, really, I could just do term-by-term integration on the Maclaurin series that we found in the previous problem. So t plus t to the 4th plus t to the 7th plus t to the 10th plus etc. The nth term being t to the 3n plus 1. Okay, why don't we do it? Just term by term. The integral, the definite integral from 0 to x of t is x squared over 2. The definite integral of t to the 4th from 0 to x is x to the 5th over 5, etc., etc., etc. Okay, so what I've done is I've computed the first four non-zero terms of the Maclaurin series for f of x, and actually I also found an nth term, even though they didn't specifically ask for that in the problem. Why would this be useful? Well, now I have a definite tool for approximating the function f to an arbitrary degree of accuracy, as long as my x value is between -1 and 1. So it's kind of cool stuff. And you guys are going to do the same thing on your homework. There's going to be situations where you're going to be asked to integrate your Taylor series, your Maclaurin series, and that's what you do. You just go term by term. Okay, then that's it for homework-based problems. I've got two more examples, and then we'll call it a day.